Episode 53, titled Nonlinearity in Data, Detecting It and Knowing When Linear Models Fail, the goal is to detect nonlinearity early so you do not spend cycles tuning a model that will keep making the same kind of error. Many workflows default to linear models because they are fast, interpretable, and often surprisingly strong, but linearity is an assumption about how effects behave. When that assumption is wrong, the model can show persistent bias that no amount of minor tweaking will fix, because the shape of the relationship itself is being misrepresented. The exam cares because it tests whether you can recognize when a straight-line assumption is a mismatch and choose a sensible next step rather than doubling down. In real work, nonlinearity shows up as frustration. Your model seems close but consistently wrong in the same regions, which is a signal about structure, not effort. When you learn to hear that signal, you save time and improve both accuracy and credibility. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Nonlinearity means that relationships are not captured by straight-line effects, which is a simple phrase with a precise implication. A straight-line effect says that each unit change in a predictor produces a constant change in the outcome, regardless of where you are on the predictor's range. Nonlinear effects violate that by changing slope, changing direction, or changing sensitivity depending on the region, so the same unit change can mean something different at low values than at high values. Nonlinearity can exist in a single predictor's effect, in interactions between predictors, or in how an outcome responds to combined conditions. The exam often uses words like diminishing returns, threshold, sharp increase, or plateau to imply nonlinearity without naming it directly. When you define nonlinearity correctly, you are also defining why linear models fail. They cannot represent changing slope without additional structure. Common nonlinear patterns include curves, thresholds, and saturation behavior, and being able to describe these patterns in words is a practical exam skill. A curve means the relationship bends, such as accelerating risk with increasing exposure, or diminishing improvements as investment grows. A threshold means the outcome changes little until a critical point is reached, after which the outcome changes rapidly, which is common in systems where capacity limits or policy triggers exist. Saturation means that increasing a predictor helps up to a point and then stops helping, which can happen with user behavior interventions, rate limiting, or control coverage, where most benefit arrives early and later effort yields smaller gains. These patterns matter because a linear model will either understate effects in one region or overstate effects in another, producing systematic miscalibration. When you recognize the pattern, you can choose a fix that matches the shape rather than forcing a straight line to act like a curve. Residual reasoning is one of the best ways to identify missed structure after fitting a simple model, because residuals expose what the model consistently fails to explain. If residuals show a systematic pattern across the predictor range, such as being positive in the middle and negative at the ends, that implies the model's functional form is wrong. A random cloud of residuals suggests that the model is capturing the main structure and that remaining error may be noise, missing variables, or irreducible uncertainty. Curved residual patterns imply nonlinearity, while residual patterns that change across segments can imply interactions or hidden confounders. The exam may describe a model that underpredicts high values and overpredicts low values, which is a verbal residual pattern indicating slope or curvature mismatch. When you learn residual reasoning, you stop treating model error as a generic problem and start treating it as diagnostic information. Transformations are a classic way to address nonlinearity, and they are often the most defensible next step when the relationship has a known shape, such as multiplicative growth or heavy tail compression. A log transformation can turn exponential-like growth into something closer to linear by compressing large values and expanding small ones, which often stabilizes variance and makes slopes more consistent. Polynomial terms can capture curvature by allowing the effect to bend, but they must be used carefully because high-degree polynomials can behave wildly at the edges and can overfit noise. Other transformations, such as square roots for count-like variance behavior, can also make relationships more linear and models more stable. The exam expects you to choose transformations because they align the data with model assumptions, not because transformations are a ritual. A good reasoning pattern is to match transformation to the observed shape and to state what the transformation is intended to accomplish in plain terms.
Tree-based models are often a strong option when interactions and thresholds dominate because they naturally represent conditional rules and step-like changes without requiring you to specify exact functional forms. If the outcome changes sharply when a feature crosses a boundary or when a combination of features is present, tree logic can capture that with splits.
Trees can also represent interactions implicitly by splitting on one feature and then splitting differently within that branch based on another feature, which aligns well with segment-specific effects.
The exam often hints at this by describing decision-like behavior, such as risk is low unless both conditions are met, which is a rule structure rather than a smooth slope.
Tree-based models are not a cure-all, because they can overfit and can be unstable without constraints, but they are well suited to threshold-driven processes.
When you choose tree-based approaches, you are choosing a representation that matches piecewise behavior instead of forcing a global linear approximation.
Splines are another conceptual tool for nonlinearity, especially when you believe the relationship is smooth and continuous rather than step-like. A spline approach fits smooth curves by connecting simple functions across ranges, allowing the slope to change gradually instead of abruptly. The practical advantage is that you can model nonlinearity without committing to a specific global polynomial shape, which can reduce edge instability and improve interpretability. Splines also support the idea that relationships can be locally different across regions of the predictor space while still being part of one coherent, smooth function. The exam may not require detailed spline mechanics, but it may test whether you recognize that smooth nonlinearity can be modeled more naturally with flexible smooth functions than with a rigid straight line. When you describe splines conceptually, you're saying that you want controlled flexibility that follows the data's curve without turning into a jagged rule set. A common mistake is forcing linearity by overfitting many engineered features, which can create the illusion of solving nonlinearity while actually building a fragile patchwork. You can create many threshold indicators, interaction terms, and transformations until a linear model fits training data extremely well, but that approach can become unstable, hard to maintain, and prone to capturing noise. It also undermines interpretability because the model becomes a collection of hacks rather than a coherent description of how effects behave. The exam often tests this by offering an answer choice that suggests adding many ad hoc features to make it work, which can be a trap when the safer approach is to choose a model family that naturally represents the structure. Engineering is valuable when it is targeted and justified by observed patterns, not when it is used to brute force fit without understanding. When you avoid forced linearity, you protect generalization and keep your modeling story coherent. Whatever approach you choose, improvements must be validated using held-out data, not training accuracy, because nonlinearity fixes can easily become overfitting if they add too much flexibility. A model that captures curvature might improve training fit dramatically, while improving validation only marginally, which indicates the added complexity is not capturing durable structure. Held-out validation also helps you compare approaches fairly, because some methods are naturally more flexible and will almost always improve in-sample fit. The exam expects you to treat held-out performance as the evidence that a change is real, because that is the test of generalization. Good validation design matters too, especially with time-ordered data, because a random split can leak future patterns and make nonlinear improvements look better than they will be in deployment. When you narrate validation here, you are emphasizing that the goal is not to fit the past perfectly, but to predict or explain reliably under the same conditions you will face later. Communicating nonlinear effects requires plain language examples and ranges, because nonlinearity often means the effect depends on where you are on the input scale. Instead of saying a feature has a single coefficient, you might describe that increasing a value from low to moderate changes the outcome a lot, while increasing from moderate to high changes it only slightly, which conveys diminishing returns. For thresholds, you can describe that the outcome remains stable until a trigger point, after which it rises quickly, which conveys risk boundaries clearly. For saturation, you can describe that benefits plateau after a certain coverage level, which supports resource allocation decisions without pretending more always helps. The exam values this because it tests whether you can interpret models responsibly, not just build them. And nonlinear interpretations require conditional language. When you communicate ranges, you also help stakeholders avoid extrapolating a local effect to the entire domain, which is a common misuse of nonlinear findings. Extrapolation risk is especially important with nonlinear models because behavior outside the data range can become unpredictable or even absurd if the model has not seen that region. A linear model extrapolates in a simple way, which can still be wrong, but at least the direction is stable. Nonlinear models can curve upward, saturate, or oscillate depending on the functional form and the learned parameters. This is why you should be cautious about making claims far beyond observed data, especially when the data is sparse at the extremes and the model's flexibility allows it to fit noise there. The exam may frame this as a warning about applying a model to a new population or a new operating regime. And the correct reasoning is that nonlinear models can be sensitive to domain shift. A safe approach is to restrict interpretation to observed ranges, monitor for drift, and avoid using the model for decisions in regions where it has little support. When you mention extrapolation risk, you are showing that you understand that model form interacts with data coverage. A practical drill for the exam is choosing the next step when you suspect nonlinearity, because the best response depends on the specific cue you observe. If you suspect a multiplicative relationship or heavy right skew, a transformation like a log can be a sensible first move because it often linearizes and stabilizes variance. If you suspect a clear threshold or strong interactions, a tree-based model or explicit interaction terms may be more appropriate because they represent conditional structure naturally. If you suspect a smooth curve without sharp breaks, spline-like flexibility can capture changing slope while preserving continuity. If you suspect that your engineered fixes are getting out of hand, stepping back and choosing a model that fits the structure directly can improve both performance and maintainability. The exam is looking for this conditional reasoning. You should not apply the same fix to every nonlinear symptom. You should match the mitigation to the pattern and validate it honestly.
A helpful anchor memory is, if residuals curve, your model misses the story.
Residual curvature is a concise signal that the model's assumed shape is leaving systematic structure unexplained.
The story is the underlying relationship pattern, such as acceleration, saturation, or threshold behavior, and residual curvature tells you that the model is narrating the wrong story, even if overall error seems acceptable.
This anchor is especially useful because it is diagnostic rather than prescriptive. It tells you when to reconsider assumptions before you decide which fix to apply.
The exam often includes residual hints in words, and this anchor helps you translate those hints into the correct conclusion that the model form is mismatched. When you remember this, you stop arguing with the data and start adapting to it.
To conclude episode 53, identify one nonlinear cue and pick a response that fits the cue and protects generalization.
A clear cue is that a simple linear model consistently underpredicts the outcome at high predictor values and overpredicts it in the middle, which is a verbal description of residual curvature indicating a missed bend in the relationship.
A sensible response is to apply a targeted transformation or add a smooth nonlinear term, then validate the improvement on held-out data to ensure the gain is real rather than an in-sample artifact.
You would communicate the result as a range-based effect, explaining that the predictor's influence changes across its scale rather than claiming one constant slope. You would also caution against extrapolating beyond the observed predictor range, because nonlinear forms can behave unpredictably where data is sparse.
This is the exam-ready pattern. Recognize the cue, choose an appropriate modeling adjustment, validate honestly, and communicate the nonlinear story with appropriate limits.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.